Hello, I'm Takeshi Kano from Tohoku University. Today I will talk with the title Adaptive One-Dimensional Crawling Robot Driven by Simple Decentralized Control Mechanism. Let me begin with the background. Many animals, such as earthworms and slugs, have a one-dimensional limbless body structure and move on various terrains by propagating a wave of expansion and contraction along the body. Inspired by these animals, many one-dimensional robots have been developed because they can be potentially used for pipe inspection, endoscopes, search and rescue operations, planetary exploration, and so on. However, there still remains room for improving the control schemes of one-dimensional crawling robots to make them more adaptive to the environment. So in this study, we propose a decentralized control scheme for one-dimensional crawling robot and demonstrate its applicability through real-world experiments. We believe that this study will contribute to engineering application as well as to understanding the essential mechanism underlying lifelike behavior. This shows the overview of the robot. The robot consists of 4 identical segments concatenated one-dimensionally. This schematic shows section view of 2 segments. Each segment consists of the upper and lower parts. In the upper part, a dynamic cell motor is attached, which is connected to a pinion lock mechanism. By controlling the motor torque, expansion or contraction force can be generated. In the lower part, the bottom of the segment is covered with a cortex material to implement a frictional anisotropy. Namely, the friction coefficient to the forward direction is smaller than that to the backward direction. A load cell is attached between the upper and lower parts to measure the reaction force from the environment. The motor torque is controlled by this equation. The basic idea is very simple. First, the reaction force SI is measured at each segment. When the reaction force to the moving direction is detected, contraction forces are generated at several posterior segments so that the posterior body part is pulled forward. In contrast, expansion forces are generated at several anterior segments so that the anterior body part is pushed forward. Thus, for example, when there is a high friction area as shown in this figure, the robot can exploit this area as scaffolds, like this. Another important point is that the actuation force converges to zero when no reaction force is generated, no reaction force is detected. Accordingly, on a downslope, actuation force is not generated and the robot is expected to slip down without any actuation. We performed an experiment using the robot developed. The robot first moved on a flat terrain, but the inclination angle is changed during the locomotion. As you can see, the robot slips down a slope without any actuation. These graphs show the time evolution of the actuation force and the segment length for each segment. As you can see, the actuation force remains zero when the robot is on a downslope. Again, we would like to emphasize that the robot autonomously changed the locomotion patterns adapting to the environment in real time. In the previous earthworm-like robots, each segment was actuated periodically at any time. However, our robot is different. We first demonstrated that the robot can slip down on a slope without any actuation. The robot is actuated at the right timing and right place. As future works, we would like to increase the number of segments. We would also like to investigate the applicability to more complex terrains. If you want to ask more details, please come to my session room. Thank you for listening to my presentation.